Topic about reducing a force moment to a single force. Let's first look at this. Concurrent force system. What's concurrent force system? Basically, say the line of action intersect at a common point. So I've got force F1 with F. This should have been F1 here. So I've got an F1, a line passes, that's the line of action. I've got F2, its line of action is here. I've got F4, line of action here, and F3, line of action. If the line of action passes through a single point, it's called a concurrent force system. It says here, this force system produces no moment about point O, naturally because there's no perpendicular distance. And the equivalent system can be presented by a single resultant force, that is F. So sum of all the forces equals 0. And so remember, if you've got concurrent forces acting on the system, there's no moment. It's just very obvious.
Sir, your
Okay,
screen isn't visible, it's just black. Like the screen is just black. It's like the diagram or the slides aren't visible.
Sir, they are visible.
Sir, they're visible.
Okay, I guess you got issue at your end then. Okay, so let's look at this. This is basically where we are going to replace. If you've got a system where you've got a lot of moments being applied and you've got forces being acting on it, you can get the resultant out by sum of all the forces, and then you can get the resultant moment out also when you do sum of all the moments. Now, in this lecture, we are going to replace even the moment with a single force. So, in simple words, the whole system will be presented by only a single force, and the effect will be the same as with the combined effect of the resultant force and the resultant moment. So let's look at in detail. Let's look at this picture here. You've got a system where you've got 4 forces being acting at different. They are not concurrent. The line of action. Look, this is the line of action here. That's another line of action. There's another line of action, and this is another. So the line of actions do not cross. So it's not concurrent. Okay. So we're looking at this picture here. We've got 4 forces being acting upon. I can take the sum of all the forces and can get a resultant moment out. You can do that. Okay. And also, if I ask you at any point, find the moment, you can also find the moment for me. There's no issue in that. So moving from this picture to this picture, you already know how to do that. Now, let's ignore this at the moment because you have already got this one out. And let's look at this picture. So we've got resultant moment, resultant force and resultant moment. What is the resultant moment? It is the turning effect. Okay. Now, on this object, I've got 2 forces. I've got the force and the moment. Let me get rid of the moment. How can I do that? So that the combined effect is the same. So look at this picture here. What we've done is we've moved the force to a certain position so that the effect is the same. So it is exactly like this one. Watch. That's a wall. I'll put hand. Okay, that's a person's hand holding this bar here. Okay, and at this point, I am applying a moment, M, and also I am applying a force F. Okay, now the force F is 10 Newton, and the moment applied is 20 Newton meter at point O. This is my point. This is my point O. This one. That's my point O. So at point O, I am applying a force of 10 Newton and a moment of 20 Newton meter. Okay. Now let me make another drawing. Can I move this one? Let's see if I can't. Okay. Okay, don't worry. Okay, let me make another here. Same thing, got a hand holding this bar, okay, and I am applying a force here, which is 10 Newton. And the distance here is 2 meters. Is there any difference between A and B scenario? That's the point O. So at point O, let's look at object A. Let's do sum of all the forces in vertical direction. So what's the resultant? What's the sum of all the forces for A in vertical direction? What's the answer?
10 newtons.
10 Newton. Now, what about in scenario? What about in scenario B? What is the sum of all the forces in the vertical direction?
That's still 10.
That's 10. So sum of all the forces, horizontal forces are 0 in both cases. So if I say FR, the resultant force for A and B are same. Am I right?
Yes, sir.
Okay, let's now look at scenario A and look at the moment applied at point O. So the effect of 10 Newton force, does not create any moment because the line of action passes through the point O. So the net moment at point O for scenario A, moment for scenario A at O would be 20 Newton meter. Am I right?
Yes, sir.
Okay, now let's look at the scenario B. So I've got moment O for B. So moment, this is my again O point given here. That's the O point. So what's the moment in scenario B for me?
20 Newton meter.
20 Newton meter. Okay, so you're telling me that scenario A and scenario B, this resultant force is the same and the resultant moment is the same. Am I right?
Yes, sir.
Okay, so let me get rid of all this. So in simple words, let me remove everything. Sorry, the force is still here. That is 10 Newton. So, sorry, 20 Newton. So if you look at object A, I've got two forces. I've got the 10 Newton force and a moment being applied at point O. But if you look at scenario B, there's only one force, that is 10 Newton. There's no moment I'm applying on it. It's the 10 Newton force that is creating the moment. So in simple words, in scenario A, I've got two active forces. I have replaced the two active forces with only one force by displacing it at a certain distance. So by moving a force at certain distance, you can create a moment. So going back to this picture here, I've got the force and I've got the moment being applied at O. I move the force at distance D to the side. I'm looking at this one now. I move the force at a distance D. And if you do the moment at point O here, the result is the same as this one. So both the pictures are the same. Is that clear to everyone?
Yes, sir.
Yes, sir.
Okay, so let's move on. Let me get rid of all this. So it says also the moment of each force about point O is perpendicular. Oh, sorry, this is basically what is. You can go through this. I've already explained you all this. Okay, now let's look at it. 3D. That was 2D, so this is more like 3D. Okay, so what we've got here, I'm looking at this picture at the moment. I've got three forces being acting on it. They're not concurrent. We've got a different line of action. I can do all the sum of all the forces. There are three forces here, so I can get the resultant out. You can do that. It's basically all vertical forces, sum them up, you get your resultant out. No rocket science. Okay. Now, moment at point O, so I will see the turning effect because of this force, distance, and distance. So I can calculate the moment at point O. Okay, so you can do this. So in simple words, moving from this picture to this picture, you can do that easily. Sum of all the forces will give you this, and the moment at point O will give you this. Now, once you've got this, if now this is the turning moment. You can see the symbol here, but there's a rotation symbol here. The rotation symbol here. Now it's rotating in this direction. So what I can do is I can shift this force at a certain distance, so the effect would be the same. Because I've moved it to certain distance, so moment at point O is the same as this into this distance, which is the same as here. So in simple words, let us compare resultant force, same, no issue. Moment, the same moment I've created by displacing the resultant force at a distance, so I get the same moment effect, just like in this 2D. So from here to here, that's the resultant, and from here to here, it's just displacing the resultant to a certain distance so that it creates the same moment as the previous. Is that clear to everyone?
Yes, sir.
Okay. Now, resultant force and moments are very important when you do designing. This is some of the work that I did when we were looking at the piston rings in an engine, looking at all the forces being applied, looking at the moments being created, and looking at the thrust forces on the piston ring. So you can see a lot of forces there. The size of this piston ring, size of this piston ring is not the cross section. This is the cross section of it. So it's not more than, well, it's smaller than this. It's like 3 millimeters. That would be cross section, smaller than this. On this size of a cross section of piston ring, you can see the number of forces being applied. So in design, for design purpose, you can see how much in detail you have to do the analysis. And we're looking at all the moments being created at different points, looking at the tilt of the piston ring, and which is very much important when you're designing pistons. And similar kind of analysis you do on the engine for the designing of the connecting rod, bearing and crank pin. Crank pin is here as your connecting rod. So a lot of forces. So remember, if you get your forces and moments right, you can design even engines. So that's basically very practical use of where we use such concepts by moving the moment to a certain distance, so that moving the forces to a certain distance so that it creates the same